Hello everyone, my name is Mohammad Alimadadi and I'm in this presentation I'll provide an overview of solar cells. I'll cover the underlying physics, materials, and performance metric, fabrication methods, loss mechanism, and current research trends. The goal is to give a clear picture of where the field is today and where it is heading. So the motivation for studying and improving solar cells comes primarily from the global transition to renewable energy. Solar radiation is by far the most abundant energy source available. To meet growing energy demand and reduce carbon emissions, improving photovoltaic efficiency and reducing costs are essential. This makes solar technology a strategic research area for both academic and industrial communities. As you can see in the right picture, the demand for the energy consumption is rising, especially in the area of Asia, China, and in America. So we need more energy, especially for AI. At the core, a solar cell operates by absorbing photons with energy above the semiconductor band gap. This generates electron-hole pairs, a built-in electric field at the junction then separates these carriers before they recombine. When an external circuit is connected, the carriers flow, producing usable electric power. All of this is fundamentally governed by semiconductor physics. So the basic is you have a p-dop region and n-dop region, and in the middle you have depletion that you make an electric field, and from this area you can kind of have a diode. Most solar cells rely on a p-n junction. At the interface, charge diffusion creates a depletion region and a built-in electric field. Current in the devices is determined by both drift and diffusion mechanism, and the IV relationship follows the diode equation. Key parameters like the open circuit voltage and short circuit current originates from this underlying physics. So as you can see here, this is an IV curve for the diode. By increasing the forward voltage, you go higher, and then after you have exponential term, and if you make the voltage negative, you have then a breakdown or avalanche region. There are several important metrics used to evaluate solar cells. Power conversion efficiency is the most central one, defined by the ratio of electrical output to optical input. Fill factor describes the quality of the IV curve. Quantum efficiency metrics like EQE and IQE measure how effectively photons generate current. Finally, the Shockley-Kayser limit sets the theoretical maximum efficiency for single junction cells. So, about Shockley-Kayser limit, theoretical maximum efficiency of a solar cell, it would be around 1 to 1.45 electron volt. This corresponds to around 800 to 1200 nanometer near infrared light. This means that this area, these wavelengths, have the greatest potential to form an efficient single junction cells. And on the left side, you would see internal quantum efficiency and external quantum efficiency over the wavelengths for the IQE and EQE and reflectance. A variety of materials are used in photovoltaic devices. Silicon dominates the market due to its maturity and reliability. Thin films like cadmium telluride and 6 offer lower cost manufacturing routes. Organic photovoltaics provide flexibility but typically lower stability. Perovskite solar cells have rapidly emerged with high efficiencies and ease of fabrication. Finally, tandem architectures combine materials to exceed the efficiency limits of single junction devices. So, for the fabrication techniques, a wide range of fabrication techniques are used depending on the material system. Traditional semiconductor techniques like CVD and PVD are used for silicon and thin films. Uh, Spin coating is also popular in research for perovskites and organics. Lithography defines the contact and patterning structure, and surface texturing is often employed for enhanced light absorption. So, at the left part, we can see how a PVD system works. The middle one is a spin coating, and the right picture, we can see how a light trapping in thin film of solar cell, how it does work based on the lambda. Understanding losses is crucial for improving device efficiency. Optical losses occur when light is reflected or passes through the device without absorption. Recombination losses include radiative recombination, Shockley-Reed Hall defects, and Auger processes at high carrier densities. Resistive losses arise from poor contacts or material conductivity. Thermalization losses result when high energy photon loss, excess energy acid. So, in the solar cells, uh, around 76.2% of total energy can arrive to the solar cells. Some problems like shading, thermal, array mismatch, dust, reflection, DC cable losses, spectral losses or inverter or AC cable and irradiation, all of them degrade our light. Recent research has produced exciting breakthrough. Perovskite silicon tandem cells have exceeded 30% efficiency, surpassing the single junction limit. Passivating contact structures such as TOPCon and heterojunction minimize recombination. A major research focus is long-term stability and understanding degradation mechanism. Finally, a scaling up fabrication method is essential for commercial viability. So on the left side, we can see the TOPCon architecture that we have anti-reflection layer, silicon nitride, and passivating layer. In conclusion, solar cells represent one of the most important technologies in the global energy landscape. Advances in material science, device physics, and fabrication continues to push efficiency upward. Although challenges like stability and manufacturing remain, the field is rapidly progressing. And this creates exciting opportunity for future research.